Good morning. Today I'm presenting the paper ENIGMA-51 towards a fine-grained understanding of human behavior in industrial scenarios. The authors of this paper are Francesco Ragusa, Rosario Leonardi, Michele Mazzamuto, Claudia Bonanno, Rosario Scavo, Antonino Furnari, and Giovanni Farinella. The ability to model human-object interactions from real-world observations is crucial. Utilizing smart cameras such as smart glasses enables our system to anticipate and understand user actions. This predictive capability not only enhances assistance but also proves invaluable in preventing mistakes and ensuring worker safety. For instance, during maintenance procedures, our AI assistants can identify user-object interactions, provide technical information, offer step-by-step instructions, issue safety alerts, and suggest the next course of action. In this context, domain-specific datasets such as our proposed ENIGMA-51 play a significant role contributing to the system's effectiveness in a real-world scenario. In recent years, numerous datasets have been introduced to advance our understanding of human interaction. Among these, the Epic Kitchens dataset features egocentric videos capturing natural activities within kitchen environments. Assembly 101 simulates an industrial context, offering assembly and disassembly videos of toy vehicles from various perspectives, including both static and egocentric viewpoints. The Ego4D dataset is expansive, encompassing 3,000 hours of daily life activity videos captured in diverse settings, equipped with detailed annotations for tasks related to past, present, and future understanding. Meccano presents multimodal egocentric data recorded in an industrial-like domain, focusing on subjects reconstructing a toy motorbike model. To systematically explore human behavior and interactions with objects in an industrial context, we introduced the ENIGMA-51 dataset. This collection comprises finely detailed egocentric videos complemented by comprehensive annotations, facilitating a thorough study of human activities in this specific domain. ENIGMA-51 is a new dataset composed of 51 egocentric videos acquired in an industrial environment which simulates a real industrial laboratory. The dataset was acquired by 19 subjects who wore a Microsoft HoloLens 2 headset and followed audio and AR instructions provided by the device to complete repairing procedures on electrical boards. The subjects interact with industrial tools such as an electric screwdriver and pliers, as well as with electronic instruments such as a power supply and the oscilloscope while executing the steps to complete a specific procedure. ENIGMA-51 has been annotated with a rich set of annotations which allow to study large variety of tasks, especially tasks related to human-object interactions. The dataset comprises 51 egocentric videos, each with a resolution of 2272 by 1278 pixels at 30 frames per second, totaling 22 hours of video recordings. It includes more than 45,000 RGB frames, 2 procedures featuring instructions for human-object interactions, more than 14,000 temporally annotated interactions specifying verbs for actions performed. Additionally, there are annotations for more than 200,000 objects and more than 56,000 hands with bounding boxes, along with more than 12,000 interaction frames annotated with more than 9,000 active objects. The dataset also encompasses more than 37,000 annotations for next object interaction in past frames, 4 basic verb classes, 25 object classes, and 3D models of the environment and objects. All the images are provided with hands and object bounding boxes, human-object interaction labels, hand and object masks obtained using SEM, and hand key points obtained using MMPose. We also acquired a complete 3D scan of the environment and the involved objects. Starting from the interaction keyframe, we sampled frames every 0.4 seconds, going backward up to 1.2 seconds before the beginning of the interaction timestamp. With this sampling strategy, we obtained more than 33,000 pass frames. We annotated the pass frame with the next object interaction annotations, which consists in a tuple class X, Y, W, H, state, TTC, where class represents the class of the object. X, Y, W, H are the 2D bounding box coordinates. State indicates if the object will be involved in an interaction, and TTC is a real number which indicates the time in seconds between the current timestamp and the beginning of the interaction. Based on the instructions used for the acquisition of the datasets, we collected 265 textual utterances, which represent the types of questions that a worker might pose to a supervisor colleague while following a procedure within an industrial setting. Figure on the left shows the verbs distribution in the 51 videos. On the right, the distribution of the objects is showed, We considered 25 object classes, which include both fixed and movable objects. Each object annotation consists in a tuple class x, y, w, h state, where class represents the class of the object. X, y, w, h are the 2D coordinates which define the bounding box around the object in the frame, and the state indicates if the object is involved in an interaction or not, active object versus passive object. With this annotation procedure, we annotated more than 200,000 objects. We provide benchmarks on 4 tasks related to human behavior: untrimmed temporal detection of human-object interactions, egocentric human-object interaction detection, short-term object interaction anticipation, and natural language understanding of intents and entities. Baseline results show that the ENIGMA-51 dataset poses a challenging benchmark to study human behavior in industrial scenarios. We considered the problem of detecting 4 basic human-object interactions: take, release, first contact, and the contact from the untrimmed egocentric videos of the ENIGMA-51 dataset. Differently from the standard definition of untrimmed action detection, in this task, a prediction is represented as a tuple C hat, TK hat, S, where C hat and TK hat are respectively the predicted class and key timestamp, the timestamp of the interaction keyframe, and S is a confidence score. We obtained an MP map values of 41.45%, 66.41%, and 35.93% respectively for take versus release, first contact versus the contact, and all interactions. The results highlight that detecting take and release interactions first row are more challenging compared to finding first contact and the contact interactions, 41.45% versus 66.41% due to the different semantic complexity. We consider the problem of detecting egocentric human-object interactions from egocentric RGB images. Giving an input image, the aim is to predict the triplet hand contact state, active object. The results show that the baseline achieved an AP hand of 90.81%, an AP hand plus side of 90.35%, an MAP H plus state of 73.31%, a MAP H plus object of 46.51%, and a MAP H plus all of 46.24%, pointing out that the use of domain-specific data in training is needed to exploit the knowledge of the industrial objects to support workers in the industrial domain. The short-term object interaction anticipation task aims to detect and localize the next active objects, to predict the verb that describes the future action, and to determine when the interaction will start. Stillfast obtains a noun top 5 MAP of 78.79%, demonstrating the ability to detect and classify the next active objects, processing images and videos simultaneously. When verbs and time to contact are predicted, performance drops according to noun plus verb top 5 MAP of 62.58%, noun plus TTC top 5 MAP of 35.77%, and overall top 5 MAP of 27.83%. We considered the problem of classifying the intent of a user utterance falling into one of the considered 24 classes, as well as the problem of entity slot filling, including 4 different slot types: object, board, component, and procedure. 5 different variants of the training data were explored: real data plus G10 data, real data plus G50 data, real data plus G100 data, and just G100. The best results for the intent classification have been obtained using only real data, obtaining an accuracy of 0.867 and an F1 score of 0.844. In preparation for future, we are expanding our dataset to encompass third-person videos, augmenting our collection to consist of 196 egocentric and 196 exocentric perspectives. This expansion is aimed to tackling the challenging ego-exo scenario. Given the procedural nature of the task, we are currently labeling the dataset with key states and mistake annotations. We proposed ENIGMA-51, a new egocentric dataset acquired in an industrial environment and densely annotated to study human behavior. In addition, we performed baseline experiments aimed to study different aspects of human behavior in the industrial domain, addressing 4 tasks. Existing methods show promising results, but are still far from reaching reasonable performance to build an intelligent assistant able to support workers in the industrial domain. Thank you for your attention.